Hi everybody, welcome back. So today we're going to start covering section 7.3, which is trigonometric substitution. Now, when we look at trigonometric substitution, one of the key details that we want to focus on is working with the equation of any circle centered at 0, 0 with any given radius. So really quickly here, I'm just going to write down x squared plus y squared is equal to r squared. Now, if you recall, this is the equation of the circle centered at 0, 0 with some random given radius r. Now, for the purposes of this example, or this section, I'm going to just rewrite this. Instead of having r squared, I'm going to have a squared here, and then we're going to have a radius of a. Good. Now, because we have this, we could then start generating this graph, and we can start viewing this circle on the grid. There we are. Now, all of these are intersecting at their corresponding A components. So if we wanted to, we could then say, take this equation here, and what we want to do is we want to solve for y. And the reason we want to do that is because we want to be able to extract a function out of this. So we would be left with y squared is equal to a squared minus x squared, and then finally arriving at y is equal to the positive or negative square root of a squared minus x squared. Now, this is a good place of where we want to be at. More specifically, just because of what we see taking place here. Now, for the purposes of this example, I'm going to go ahead and I'm only going to talk about this top portion of this equation. So the top portion of this equation is just going to be the positive version of this square root. In other words, the principal square root. So what I'm looking at here is I'm looking at a function which is defined as the square root of a squared minus x squared. And I want something or some way to think about this as a function that depends on a different variable that is not x. Now, one of the things that we learned from trig is that anytime that we have some sort of circle, we can always parameterize using some theta and some r value, in this case some square value or some radius value. So what I'm going to do here is I'm going to say really quickly, let x equal to a times cosine of theta. Now, by doing this, I'm now creating this substitution. Oops, excuse me here. There we go. Now, by doing this, I'm creating this substitution here where I'm going to have a squared minus the quantity of a times cosine theta squared, which means I will have a squared minus a squared times cosine squared theta. And I'm going to take the square root of that. Now notice these first two terms, or these two terms here, have a common factor of a squared. So if we factor out that common factor of a squared, then we're left with a squared times 1 minus cosine squared theta, as such. Now, if we keep going with this whole process, we could then say, hey, let's go ahead and let's evaluate this a little bit further. Taking the absolute value, or sorry, taking the square root of a squared, that's going to leave us with the absolute value of a multiplied by the square root of 1 minus cosine squared theta. But notice that the radicand, that 1 minus cosine squared, that's actually a Pythagorean identity. And that Pythagorean identity, if you remember, can look like cosine squared theta plus sine squared theta is equal to 1, which means 1 minus cosine squared is really just 1 or excuse me, is just really sine squared theta, like such. Now, having this, if we naturally think about this, when we talk about the radius is always going to be positive. Therefore, when we're looking at this value here, the absolute value of A, there's no reason to have the absolute values because, again, under the assumption, signifies a radius, therefore positive. Now, square root of sine squared. Now, square root of sine squared is not that straightforward because this does evaluate into the absolute value of sine of theta. However, if you focus on the top part of the circle that we were viewing here, that top part for all of those sine values is always going to be positive, right? Because you're always looking for the ratio for some angle within the first or second quadrant. Therefore, sine of any angle within the first or second quadrant will always be positive. Therefore, once again, we don't need the absolute values, and we naturally get A times sine of theta. And this is a new function that we work with. All right, this is us defining a new function that is dependent on not the variable x, but the variable theta. Now, you might be saying, well, why do we need this at this point in time, right? Well, there's a reason as to why we need this and why we need to define it this way. All right, what I'm going to do here is I'm going to build these expressions. I'm going to build these expressions, and I'm also going to build the substitution that is going to be needed. So the first expression, any time that we run across an integrand, and the integrand has an expression of the form square root of a squared minus x squared, then the natural substitution that we're going to be looking at is going to be a times sine of theta. But if you remember from trig, this is actually going to tell us that sine inverse of x over a is equal to theta, which will allow us to find these theta values. But again, remembering or recalling trig, sine inverse is actually bounded between negative pi halves and pi halves. So we have to be really careful when we make these substitutions that we must always abide by these restrictions. Now, similarly, if we ever see in the integrand some form of square root of a squared plus x squared, the natural substitution that we want to make is going to be x is equal to a times tangent of theta. Now, very similarly, this will then give us that tangent inverse of x over a will be equal to some theta, but then again, tan inverse, then again, tan inverse is also bounded between negative pi halves and pi halves. And you're absolutely right that that is non-inclusive. Whoops, here we go. There we are. Whoa. All right, so here we are. Let me fix this really quickly. There we go. Perfect. There we are. So the last scenario that we're going to discuss here is when the integrand contains an expression of the form x squared minus a squared. The natural substitution that we're going to want here is a times secant of theta. And this theta value is a little bit trickier to see because if you remember secant is a reciprocal identity for cosine. which means we have to abide by the cosine restrictions. Once we abide by the cosine restrictions, we then just have to make sure that we don't run across any asymptotes when we're going through this process. All right, so I put these in red specifically because these are going to be the equations that we're going to be using, and they're going to be the ones that we want to focus on. All right, these are super uber important for our class moving forward. So we must know these at all times. Awesome. So now that we have this down, let's go on to an example. All right, so here goes your first example. And what we want to do is we want to evaluate these integrals. And here goes part A. We want to evaluate the integral for x squared divided by the square root of 9 minus x squared. And this is all dx. All right, so again, the first thing that we see, or that we should be able to see, is that identifying the denominator, identifying the denominator. Looking at the denominator, we then see that we have that radicand, or that radical of 9 minus x squared, where the radicand is 9 minus x squared. So just by identifying that, we can use a substitution that we saw previously, and saying that that could be the half of the circle that we want to see. Therefore, we're going to say let x be equal to 3 sine theta. Now, making this substitution, again, we have to recall the substitution rules from Calc 1. Substitution rules say that if you define your x value, you also need to, you define your x value with respect to dx, then you also need to find what your d theta, or your d substitution, will be. And in this case, it will be 3 cosine theta d theta. Awesome. Now, I'm going to go ahead and make those substitutions on this integral. My x value is now 3 sine theta, that's squared, divided by square root of 9 minus 3 sine theta squared. Take that radical. And then dx. According to our dx is 3 times cosine squared d theta. Now, one of the items that I'm going to ask you to remember is always remember that substitution variable. It's going to be very, very crucial that we always consider the dx to be based upon the substitution that we made. Now, moving through this whole process. Numerator, we're now going to have 3 squared, that's going to be 9, times another 3, that's going to be 27. So that's 27 times cosine theta times sine squared theta, all divided by, we're going to have 9 minus 9 squared times sine squared theta. So that's going to be the square root of 9. I'm going to factor that 9 out, and we're going to get 1 minus sine squared theta. And this is all d theta. All right, so in the denominator, we're going to take the square root of 9. So that's going to get us a 3. So naturally, the constant that we have will be 27 over 3. Factor that constant out of the integral. And then we're left with cosine theta, sine squared theta, all divided by the square root of 1 minus sine squared theta. And this is all d theta. Now you can say, okay, hey, Mr. Castro, what about that denominator? You're going to say, I see a Pythagorean identity down there. And you're absolutely right, to whoever said that. All right, so we're going to have cosine theta times sine squared theta, all divided by the Pythagorean identity in the denominator, which will be the square root of cosine squared theta. Now again, you got to be careful, right, when you're considering this for cosine squared theta. We got to make sure that cosine squared theta will always be positive if we want to evaluate this integral. So let's see if we can then go through the restriction. the restriction here was that x was equal to 3 sine theta, which means if we're doing these restrictions for theta, then sine inverse will be between negative pi halves and pi halves. Now, that's really nice because working with this part here, and let's see here, working with this part, would you agree that theta bounded between negative pi halves and pi halves is really just identifying quadrants 1 and quadrants 4? Think about cosine of theta values within those quadrants. Any cosine values of those angles will always give you some positive value within quadrants 1 and quadrant 4. Therefore, we kind of maneuvered our way to say that our integrand is now cosine theta times sine squared theta divided by cosine theta. And you're going to see here, well, great, because at this point in time, we can now simplify that integrand. So, as this all follows now, this is 9 times the integral of sine squared theta d theta. And this is where we want to be, because at this point in time, the integral of sine squared theta, we could just use a power reduction rule. So I'm just going to really quickly write on here that we need a power reduction. So power reduction for sine squared. Now, I know you guys are keeping up with the work, and I know that you guys are studying super duper uber hard, which means you will automatically be able to extract that sine squared theta is equal to 1/2 multiplied by 1 minus cosine of 2 theta. If you had that in your back pocket, awesome. Not literally, but figuratively. All right. Man, I wish somebody would laugh at my jokes here. That would be super awesome. Aw, thank you. Well, that was funny. Awesome. I like that. All right, so here now we have 9 times the integral of our power reduction, which was 1/2 multiplied by 1 minus cosine 2 theta, and this is all d theta. Now working through the whole process, I'm going to factor out that 1/2, and then I'll go ahead and I'll integrate term by term. The integral of 1 with respect to theta gets us theta. The integral of cosine 2 theta will then get us 1/2 multiplied by sine of 2 theta. There we go. And I just need a plus c because this is an indefinite integral. All right. So if you're here, awesome. Good so far. Now let's keep going. All right, I'm going to distribute my parentheses here. So this is going to get me 9 over 2 times theta minus 9 over 4 multiplied by sine of 2 theta. Now, to the normal person, you might say, oh, wow, I'm finally done. But then to the more advanced person, they might actually say, well, you're not really done just yet, simply because you solved the integral that we initially had. However, you gave the answer in terms of theta. Now remember, the initial integral was in terms of x, so we have to go back and give the integral in terms of x, or the answer in terms of x. So we still have a little bit more to do. All right, so this is not the final answer. Not the final answer. All right, it's not the final form. All right, we haven't gotten there yet. So we then need to convert thetas into x's and any sine identities that we see back into x's or back into y's, whatever that may be. Again, more preferably x's because that's what we're working with. So let's see if we can then keep going with this. All right, so here we go. I'm going to bring this down here. All right, so the answer that we have so far is 9/2 theta minus 9/4 sine of 2 theta plus c. Nice. All right. Now, I'm going to go back and I'm going to recall this substitution that we made at the very beginning. The substitution that we made at the very beginning was right up here, which was x is equal to 3 sine theta. So I'm going to use that. X is equal to 3 sine theta. And the reason I'm going to use this is because this equation, or this substitution, actually gives me what I need for theta. Look at what it gives me here. I get that sine of theta is equal to x over 3. Thinking back from trig, that's actually some right triangle with some angle theta whose sine ratio is x over 3. In other words, if I identify the angle within that right triangle, it's ratio-wise opposite over adjacent side. So I'm going to kind of keep that in our back pocket just really quickly, and I'm going to keep going back to this part here where I'm trying to solve for theta. Solving for theta means that we have to take the sine inverse of x over 3. And that actually solves our first issue that we didn't know what theta was. Theta, we have that representation now. Theta is sine inverse of x over 3. Now we have to break down sine of 2 theta. So we can't directly go with sine of 2 theta unless we use some, let's say, half angle identity. All right, we could use a half angle, or we can go to a double angle. Now, you might say, well, double angle might be a little bit quicker, and I would agree that this double angle for sine of 2 theta would actually be way easier. It's actually an easier route to take. Now notice that when we do the double angle, we have to know what is sine of theta and we have to know what is cosine of theta. The nice part is that we know what sine of theta is. The only thing that we don't know is what is cosine of theta. But according to cosine of theta, that's actually going to be real nice, because looking at our picture here, we can actually derive what cosine of theta is going to be. Would you agree that solving for this missing side, it would be the square root of 9 minus x squared? Now, does that kind of look familiar? I don't know. Might kind of look familiar somewhere. Denominator. All right. So, excuse me, I had to clear my throat there. All right, so once I have this, I can now say, well, hey, look, the cosine of that angle is just square root of 9 minus x squared, all divided by 3. Therefore, when I rewrite my answer in terms of x, I now have the first term to be that 9 halves times sine inverse of x over 3 minus, remember that 9 fourths is multiplying the 2, therefore we get 9 halves, multiplied by sine. Sine was x divided by 3, multiplied by cosine. Cosine was the square root of 9 minus x squared divided by 3. And again, don't forget that constant. And believe it or not, we're already there. I know it's been quite a wild ride, but we're finally at the end of the first example. Look at that. You're proud of yourselves? Give yourself a pat on the back. And yes, I am giving myself a pat on the back right now. All right, so here's our final answer. At the end of the day, this is what we want to see. Your answer of that initial integral, which was the integral of x squared divided by the square root of 9 minus x squared all dx, can finally be resolved as this as your final answer. All right. So I'm actually going to put a pause on this video and I'm going to go through a different example, and working with those different examples we'll actually get to see how we're going to keep using all of those substitutions that I listed at the very beginning of this video right here, the ones that were all scribbled in highlighted yellow. All right, so I'm going to put pause really quick and then we'll come back and we'll do the next example. All right, welcome back. So we're going to start on part B. All right, so let's go with part B. Part B on this example, again, we still want to evaluate this integral. And this is now going to be the integral from 0 to 3 for x divided by the square root of 36 minus x squared, and this is all dx. All right, so let's start working with our newfound substitutions. The substitution that I want at this point in time is going to be that x is 6 sine theta. Now, if x is 6 sine theta, then naturally our dx will then be 6 cosine theta d theta. Nice. So let's go ahead and let's make these substitutions. So making these substitutions then, x was our 6 sine theta, that's the x value, divided by the square root of 36 minus the x value, which was 6 sine theta, quantity squared, multiplied by dx, but dx we know to be 6 cosine theta d theta. Now notice I left the limits of integration blank. And I left the limits of integration blank specifically because we have to find new limits of integration. All right. Now, the limits of integration are based on the x values. So when I say that x was equal to 3 and x is equal to 0, those are the bounds for the x values. Now I have to think of bounds, but in this case, I have to think of the bounds for the theta values that I'm looking at here. In order to do that, we're going to use the substitutions that we had. If x is equal to if x is equal to 0, then the first substitution will give me that 0 is equal to 6 times sine of theta, which means 0 is equal to sine of theta, which means what is theta? Theta naturally must be, yeah, you guessed it, 0. Great. Now what happens if x is 3? All right, our upper limit of integration. If x is 3, then making our substitution into x is equal to 6 sine theta, that's going to be 3 is equal to 6 sine theta, which means we get 1/2 for sine theta. Now, theta, or sine of theta, to be equal to 1/2 actually gets us a value of pi 6, which means our new limit of integration, our upper limit of integration, should be pi 6. So upper limit of integration is pi 6, lower limit of integration should be 0. Therefore, we can go through and keep making our substitution. All right, let's go. All right, that's now going to be the integral from 0 to pi 6. Let's multiply that numerator. That's going to be 36 multiplied by sine theta, cosine theta. The denominator, after some algebra, looking at the 6 sine quantity squared, that's going to be 36 sine squared theta. Factor out the 36, and we're going to be left with 36 multiplied by 1 minus sine squared theta, all inside of that square root, and this is all d theta. Which means our integral should now be 36 divided by 6 multiplied by sine theta cosine theta divided by the square root of 1 minus sine theta. But again, if you're following with the Pythagorean identities, that Pythagorean identity in that denominator should be square root of cosine squared theta d theta. Which kind of makes it nice because, once again, identifying your restrictions, thetas can be bounded between negative pi halves and pi halves. Again, in other words, quadrants 1 and quadrants 4. Now, this kind of goes back into our bounds when we were working with this here, saying where is sine equal to 0, or what angle gives you a sine measurement of 1/2. Well, that's only working in quadrants 1 or 2 or the x-axis. So, back to what we were looking at here, this is now going to get us 36 divided by 6, that's 6, integral from 0 to pi 6, multiplied by sine theta, cosine theta, divided by cosine theta. And the reason we can say again divided by cosine theta is because in quadrants 1 and 4, cosine of theta will always be positive. So this really just turns into 6 multiplied by the integral from 0 to pi 6 of sine theta. Look at that. Really nice integral that we get. So working through this integral now, all we have to do is figure out what is the antiderivative for sine theta. That antiderivative should be negative cosine of theta, and we're going to evaluate that antiderivative from 0 to pi 6. So making that evaluation now, that's going to be negative cosine at pi 6 minus the negative, so that's going to be plus cosine at 0. Cosine at 0 we know to be 1. Negative cosine at pi 6. Doing some work there, that should be root 3 over 2. So that's going to be negative root 3 over 2 plus 1. Distribute the 6. And we get negative 6 root 3 over 2 plus 6, which naturally simplifies to be 6 minus 3 root 3 as the final answer. And there we have it. So when we're evaluating these integrals in a definite interval, when we're giving that interval, turns out that these integrals are actually slightly easier to evaluate. The hardest part is going to be when we have to do these indefinite integrals. And we'll see a little bit more of those indefinite integrals as we keep going through class. All right, so let's look at the next integral at hand. That was part B. Let's then look at part C. So here we go, part C. We want to evaluate the integral from 0 to 2 for dt over the square root of 4 plus t squared. All right, so again, looking at the substitution integrals for that table, the substitution that we want to make at this point in time, we're going to say let the variable t equal to 2 times tangent of theta. Now when we make the substitution, we then need to find out what the derivative of t is. So dt is going to be 2 times secant squared theta, d theta. And let's make those substitutions. dt, that's going to be 2 secant squared theta, d theta. Denominator, square root of 4 plus t squared. That's going to be 2 tangent of theta squared. Limits of integration, we're now going to go through the limits of integration. Limits of integration, I'm going to re-index here. So I'm going to use, when t is equal to 0, we get that 0 is equal to 2 tangent of theta, which means 0 must be equal to tangent of theta. Remembering your restrictions. Theta, let's write it here. Theta is bounded between negative pi halves and pi halves. In other words, first and fourth quadrant. Which means that for this first substitution, theta must be 0. Nice. Now what happens when t is equal to 2? Well, when t is equal to 2, then we're going to have 2 is equal to 2 tangent of theta, which means 1 is equal to tangent of theta. And the ratio for tangent, for it to be equal to 1, this must be that theta must be pi fourths, which means our upper limit of integration is just pi fourths. Nice. So we can go through and simplify now. From 0 to pi fourths, that's my integral. On here I have 2 multiplied by secant squared theta divided by, would you agree that the denominator, once we factor all that out, that's going to be 4 multiplied by 1 plus tangent squared theta. And this is all d theta. Good. But also remember that once we have this substitution, your Pythagorean identity, 1 plus tan squared, that is secant squared theta. This is your Pythagorean identity. So using that Pythagorean identity as our substitution in that denominator from 0 to pi fourths, we're going to get 2 secant squared theta divided by 4 multiplied by secant squared theta, and that is all under the square root in that denominator. Now we just have to make sure that secant squared will always be positive, or at least secant will be positive. Now if you remember secant, secant is just a reciprocal for cosine, so the big question is cosine positive under the restrictions for theta? So take a minute to process that. Look at these restrictions. Is cosine positive in those angles, through those angles? The answer should be yes. Which means if cosine's positive, then so will secant. Secant will also be positive, which means we're looking at 2 secant squared theta divided by 2 secant theta d theta. Naturally, this will simplify to be the integral from 0 to pi fourths for secant of theta d theta. Now we have to evaluate this. Now if you recall, there was some important integrals that we wanted to see. Now the class meeting before all of this happened, I wrote on the board that we were going to go through and we were going to prove, or we were going to show that anytime that we have secant x dx, that this is equal to the natural log of the absolute value of secant of x plus tangent of x plus c. Now I went through in class and I derived that, showing you that there was one specific trick that we had to do in order to get that evaluation. So using that, we're actually going to go through and say, okay, well that we know to be true, therefore this is going to be just the evaluation of natural log of secant of x plus tangent of x. Oh, excuse me, I was not using x. Wow, that was bad form on me. So secant of theta plus tangent of theta, and all of this is going to be evaluated from 0 to pi fourths. Which means evaluating this from 0 to pi fourths, this is going to be secant of pi fourths plus tangent of pi fourths minus natural log of secant of 0 plus tangent at 0. So going through, we're going to have the secant of pi fourths. Secant is a reciprocal for cosine, so all we really need is cosine at pi fourths. Cosine at pi fourths is really just root 2 over 2. So that means the inverse of that, or the reciprocal of that, is just going to be root 2. Tangent of pi fourths, that's just 1. Minus natural log secant of 0, that's 1 over cosine at 0. So that's cosine at 0 is 1, so that's 1 over 1, so it's just 1. Tangent to 0 is 0. Now you might say, hey, natural log at 1, that's just going to be 0, and you're absolutely right. And for the first term, we get the natural log of the square root of 2 plus 1. Now notice I did drop the absolute values at the end simply because our answer in the argument of this natural log will always be positive. Square root of 2 plus 1 will always give you a positive number, therefore we can drop the absolute values. But at the end of the day, this is our final answer. The initial integral that we were looking at over here at the top left corner was the integral from 0 to 2, and that was 1 divided by the square root of 4 plus t squared, all dt. At the end of the day, we were given this answer of natural log the square root of square root of 2 plus 1. Now, here's going to be a challenge for you. All right, so I'm going to write this in purple. Try to, and actually, I'll save that challenge for next time. All right, and I'll actually stop the video here. All right, so I'm going to stop the video here, and coming in on the next video, I'm going to work out part D and part E, and then hopefully you guys can work through those videos as well. I will see you next time.